In Unit 17-18, we are going to look at derivatives of specific functions, such as exponential and log functions, and then in 19 we'll look at trig functions. So we did a lot of exponential and log functions in 4U, if you remember. So we're going to do a quick review just to go over some of the properties of exponential and log functions, and also the laws of logs. So an exponential function, for example, y equals 2 to the power x, and a log function. So we're going to graph and see what they look like. So if you remember, a logarithmic function is the inverse of an exponential function. So if we want to undo an exponential function, we can log to solve exponential equations. Okay, so if you're not sure what y equals 2 to the x look like, we can make a table of values. And we'll pick a couple of positive numbers and a couple of negative numbers. So we've got 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and then 2 to the negative 1 is a half and a quarter. So I'm just going to change color here, plot a few points here. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and on the left side we get 1 half, 1 quarter, and that fraction is going to get smaller and smaller and smaller to infinity. So the x-axis is an asymptote. The line will approach 0 as we head to negative infinity. The domain is any real number. There are no restrictions. The range has a restriction. We can use any y, but y is always going to be positive. It will never get to 0. If we do the log base 2 of x, this is the inverse of y equals 2 to the x. So in order to find our points, all we have to do is switch x and y. So 0, 1 would become 1, 0, 1, 2 would become 2, 1, 4, 2, and vice versa, 1 half, negative 1, 1 quarter, negative 2. Actually, I'm going to change color here. So we'll do I will do the log or the exponential in blue just to separate. So 1, 2, and 4. So there's my y equals 2 to the x, and then we'll do the log in red. So 0, 1 became 1, 0. 1, 2 became 2, 1. And then we have 4, 2. And then on the left we have 1 half, negative 1, and 1 quarter, and so on. So now it's going to log base 2 of x is going to approach the y-axis. So in this graph, the y-axis is the asymptote, and it will approach the y-axis to negative infinity. The domain is now restricted, so the domain will be greater than 0, and the range will be any real number. So it makes sense because the inverse, we switch x and y, so it would make sense that the asymptotes will switch x and y axis. The domain and range will switch because they represent x and y. So that's what the graphs look like. You first looked at those in grade 11 and again in grade 12, so they should be familiar to you. Graphs here, we can't have a negative result. Everything is above 0, so it can't. The laws of logs we covered in 4U. So we have our change of base formula that we can use if we cannot change to the same base. So normally we would solve exponential equations or evaluate exponential functions by changing to the same base. If we can't do that, then we use the change of base formula. So for example, if I had 2 to the power x equals 5 and I could not change the same base, I could use the change of base formula by taking log of 5, the answer, divided by log of the current base. And that's how we do the change of base formula. So the log that you're using is log base 10. That is the log button on your calculator. We also have a power or a product rule. So if we have log of the same base and we are adding, we can switch that to multiplication and vice versa. We have a quotient rule. If we have log of the same base and we are subtracting, we can switch that to division. And then we have the power rule where we can bring down any exponent and multiply. So those are the 4 laws of logs that we looked at in grade 12, and they help us solve or evaluate logarithms. Negative. So here's some examples. You may be able to change the same base, maybe not. So usually we try to change the same base. So for example, log base 5 of 25, I could change 25 to 5 to the power 2. I could apply the power rule and bring down that 2. And log base 5 of 5 equals 1. Or you can change it to exponential form. That's another option. So we have base 5 to some power has a value of 25. And then we'll change 25 to base 5, so it would be 5 to the power 2. Once we have the same base, we can drop the base 5 and just state that x would be equal to 2. So you can solve within the log by changing to the same base, or you can put in exponential form and solve that way. So it depends on the question. If it's tricky, sometimes it's easier to change to exponential form, and sometimes it's not. So just remember that with log equations and exponential equations, so let's say we had a to the power x, y equals a to the power x. If I put that in log form, a is the base, that goes here, y is the answer, that goes there, and x is the exponent. So the exponent goes here, the base goes here, and then this is the result, or sometimes we call it the argument. So you should be able to easily switch back and forth between exponential and log forms. If you can't remember this, maybe it might be a good idea to go back and review your 4U notes. Hopefully you still have them. But it is an expectation that you would know how to work with exponents and logs already. So this is a little bit of a review. So I'm going to put this one in exponential. So 1/3 to some power equals 27. I want to change the same base, so I'm going to bring the 3 to the numerator. So that would be 3 to the negative 1 times x. 27 is 3 to the 3. Once I have the same base, I can drop the base, and x would equal negative 3. I'll put this in exponential. 7 to some power equals 0. Well, that is impossible. There is no solution. We can't have 7 to a power and get a result of 0. And if you think of your, sorry, excuse me. So think of 7 to the, any whole number is going to be a positive number. If x is a negative value, it's going to give me a fraction, but it's not going to get to 0. So anything equal to 0 is invalid. Anything negative is invalid. You can't get a base to a power and get a negative result. If you can't change the same base, so for example, if I put that in exponential form, I am asking 4 to what power equals 66. Well, 66 is not a multiple of 4, so I can use my change of base formula. So basically with change of base, we log both sides because we want to undo or inverse the exponential function. We bring down the x to isolate it, and then we divide to solve for x. So that I can just type into the calculator. So if I had a calculator handy, which I do not, I would just type that into the calculator and get a decimal answer. So sometimes we cannot change the same base and you'll have to rely on the change of base formula. Sometimes you can't evaluate them separately, but you could if you put them together. So here we have subtraction. So I can change subtraction back to division. And then 24 divided by 3 is 8. 8 is a multiple of 2. It's 2 to the 3. So that would equal 3 log base 2 of 2. Log base 2 of 2 is equal to 1 because 2 to the power 1 equals 2. So that equals 3. In this question, the first thing you'd want to do, you don't want to put addition back to multiplication until you bring up the exponents. So I'm going to change it to 2 to the power 2 and log 5 to the power 2. So 2 to the power 2 is 4 and 5 to the power 2 is 25. Then I'm going to change addition to multiplication. So that's 100. Now consider this log does not have a base. That's because it's base 10. So if you don't see a base, it's automatically assumed that it's log base 10. So 10 to the power 2 gives me 100. So that has a value of 2. These are also just applying log laws to solve. So here we can't change the same base. So I'm going to use my change of base formula. Log of the answer divided by log of the base. And so once you type that into the calculator, it works out to be 11.9. Same thing here, can't change the same base. So 2x would be log of the answer divided by log of the base. So I'll just type that into the calculator. And that equals log 50 divided by log 5. That equals 0.6989, and then we'll divide that by 2. So 0.349. This one I probably would put in exponential form. So 2 to the power 0 equals 3x. 2 to the power 0 equals 1. And so x equals 1/3. So you have to look at the question and decide whether you're going to use change of base formula, if you're going to use any of your laws of logs, or maybe you just put in exponential form and solve from there. In this one, I want to isolate base 2 because it has the power on it. So the first thing I'll do is get rid of this 225. So I might reduce that to a fraction. So that's 1/3. So once we have one base on each side, we can use our change of base formula. So the exponent negative x over 4 will equal log of 1/3 divided by log of 2. So we'll just type that into the calculator. And negative x over 4 equals negative 1.58. And now I have to solve for x. So I'm going to cross multiply. So we'll multiply this answer by 4. And then change the sign. So it'll be positive 6.339 approximately. Okay, in this last one, first thing I would do is change addition to multiplication. Then I'll put in exponential form. So base 6 to the power 1 equals x times x plus 1. So 6 equals x squared plus x. I want to solve for x, so let's put everything over to the right, and then we'll factor. So 3 2s are 6, so it's going to be plus 3 minus 2, and then we'll solve for x. Now one thing you have to watch out for is extraneous roots. So an extraneous root is an invalid root. So what that means is if I put my answer back in here, do I get a positive result? If I don't, if that result is negative, then it is invalid. So for example, I can't put in negative 3 because I can't have 6 to any power and end up with a negative result. So this one is invalid. So we call that an extraneous root. So any answer that does not give me a valid answer, I would eliminate. And so x equals 2 would be the only solution.